Hello Abaqus user, welcome to Abaqus Acumen for quick and sound learning. Today's session we are going to do a bird strike analysis. The bird is going to model using a smooth particle hydrodynamics and its goes and impact on the aluminum plate. So right now what you are seeing is a bird which is most of the time idealized as a water body. So 5 kg of bird water body is going to hit to aluminum plate, and the bird is get into a different small particles. So this is a problem we are going to do. It will be very easy and interesting for you to learn more about the smooth particle hydrodynamics. Abaqus is very robust software in case of a fluid structure interaction. So we are going to do this problem. So just quickly go through the initial slides. So a smooth particle hydrodynamics modeling for an impact problem. This is what exactly we are going to do. We are going to do a bird strike analysis in Abaqus explicit. Just a quick overview on the SPH modeling. SPH modeling is available from Abaqus version 6.11. But 6.11 you have some when you have to model with a SPH, you have to do build a mass element, then convert into PC 3D. So it's a bit tedious with 6.11, but from 6.12 there is no issue for this conversion. So in today's session you'll also learn how to convert this solid element into PC 3D. So water body or a smooth particle hydrodynamics element, how you can do this. Now, what is a smooth particle hydrodynamics? SPH is actually a meshless Lagrangian technique based on the interpolation theory and smoothing kernel functional. So it is nothing but is a meshless node based body or part you can model a node based. So there is no mesh. So there are a lot of advantage when you don't have a meshless Lagrangian technique. Fluid is represented in this particular case as a set of discrete interacting particles which can be independent from the Lagrangian element. So it's just a discrete integrating particles. No mesh distortion for fluid. Since there is no mesh, so you don't get into this mesh distortion issues. No solution domain to define a special mesh for the fluid. The method provides more accurate result than Lagrangian. It is obvious because you have Lagrangian mesh where element get distorted. As element get distorted, your result accuracy go down. So in this particular case it is a meshless, so your accuracy is better. Also people claim that CEL which is couple Eulerian Lagrangian analysis, which is also available within Abaqus as a fluid structure interaction or a high deformation and problem solving technique. It's claimed that SPH is better than this when deformation is too severe. Now going back to the application of SPH modeling, effective for application involve the extreme deformation. Instead of CL, SPH can be cost effective because for CL you take a lot of computational time. SPH is very fast, quick. You can do a lot of example problem, fluid sloshing, wave energy, ballistic, spray, as in paint industry, gas flow. You can do multiple problem here. We are going to concentrate something on the ballistic problem, similar like ballistic, but it's a bird strike analysis. So getting down to the problem definition, this will be very simple problem. This is built-in video. Just understand how you can make a SPH body, how you can use contact, and understand how the bird strike analysis on a flat plate. Then later on you can build on a different curved surface, canopy, turbine, rotating turbine hit with a bird strike. So this particular problem is a soft body, 5 kg of birds. It's going to hit with 100 meters per second on a aluminum plate, 1 meter by 1 meter plate with a 3.5 millimeter thickness. All these extreme outer edges will be constrained. Bird is going to analyze. Typically bird is a water plus air. So 90% water, 10% air. People use this gelatin as a material. Since it is a 90% water body, a lot of people assume it as a water. So again, how to the bird shape and the bird size, there are different papers available. You can have a circular cylindrical bird with typical length to diameter ratio, or you have bird with a hemispherical end. There are a lot of literature available. We are going to just build with a simple bird representation here. We are going to put a Cylindrical bird with length to diameter ratio around 1.56. So the diameter is 160 millimeter, length is around 250 millimeter. Bird will be hit with 100 meters per second velocity, which is quite lower velocity we had taken. But in actual bird strike analysis, when bird hit on a aerospace wing or canopy, it hit with around 440 meters per second. So you can model with that. And the bird we are going to model with a smooth particle hydrodynamics particle element, so it's a PC3D. Just quick on the unit side, units we are going to use ton, millimeter, newton and second. The bottom plate, aluminum plate, we are going to put a end caster condition on the edges. Bird will hit with 100 meters per second velocity. The typical bird property density will be 940 kg per meter cube. Here we have put in a ton per millimeter cube. You will have some equation of state. Equation of state is nothing but your volumetric strain. So pressure versus volume ratio, volumetric relation is people. For the fluid structure, you need to fluid modeling, you need to give this equation of state, which is a pressure versus volumetric strain equation. Now for typical water body, it is a speed of wave within water body, which is 1.1450 meter per second. So we are going to use that as a equation of state. We are going to give some dynamic viscosity 1 e power 0.5. The bottom plate will be aluminum with typical 2770 kg per meter cube, density 73.1 GPa as a modulus, and then we will give some plasticity strain in this. So let's quickly start building this model. So we'll quickly build this. Let me set the directory. So I just set the directory. So first we'll quickly create a bird. So bird, we'll go to 3D, type deformable solid resolution. I'll go for 500 as acronym size. I'll put first 0, 0. Then we'll have 160 as diameter, so 80, 0. I got 1 point, and then I'll 80, 250. So I got another point at the top, and then I'll have one more 0, 250. I'll quickly put a line here. That's all I've done, and then I'll say revolve this around 360. So I just quickly created the bird body, a solid cylinder here I created. Now for meshing purpose, I need to split this for a quite transactional mesh. So I'm going to cut it. So in the same part module, I'm going to go to partition cell, define cutting plane, where I'm going to go, and here I'm going to get a normal to edge. So I'm going to select this edge, this as a point. I'm going to, from the middle, I'm going to cut it into two parts. This is just guys for a meshing purpose, to get a more structural mesh. Second thing, I'm going to go to property. I'll first create, water. So first I need to have density. So typical what we are going to give is a 0.94 e power minus 0.9 as a density. And 1 minute, I'll just quickly check what is the density. So 9.4 e power 10, then (0.94 e power 0.10). So it is less than 1000 kg per meter cube. Then we'll have EOS, and then I will have viscosity. EOS will put as a USUP, so 1450 e power 03. This will be 0. S and gamma will be 0. So you will get a lot of detail on this. And then viscosity will put 1 e power minus 9. Let me check viscosity. Yeah, so we have done that. I'll quickly create water, homogeneous solid. I'll say water. We have created water. We'll just assign this to cylindrical part. So we assign this. So we quickly created the bird geometry and we assign the property. Now we'll quickly create another part. Deformable shell will get a planar. So we'll say this aluminum. So we'll put AL is a planar. So approximate size I'm putting 2000 because it will be 1 meter by 1 meter, so 1000 by 1000. So we done that. We'll just quickly put 0 comma 0 and then I'll just put two corner 500 comma 500 minus 500 comma minus 500. So I'll just fit this. So I'll use this rectangular, so I have this point and then this point. Now I'm done. So I quickly done this. Property will create for aluminum. I say aluminum, then you give density which is 2.77 e power minus 9. Then you'll give elasticity. It will be 73.1 e power 03. Poisson's ratio 0.33 we are given. Now we'll give a plasticity. Plasticity will give 170 as a yield, and then 340 will have a 10% strain. So it is almost like a tangent modules also, you can say. So we've done that. We'll create now thickness for aluminum part, shell thickness. So it will be 3.5 millimeter, and the aluminum one will select, and we'll assign this to the plate. So we created now both part. We are not mesh still. We created a bird body, we created aluminum. Now we'll just quickly make an instant out of these two. So we have created instant. Now I need to rotate the bird body because they're in the same plane. So in the same panel I'll just rotate this instant. So the bird, I'll say, so I have to rotate this about x-axis. So 0 0 is fine, then I'll put 1 comma 0 comma 0, so it will take a x-axis, and I'll say 90. So I've done this. So let me see in some view. So it is just touching the plate. We'll just move this to avoid a penetration. So we'll move this by 0 comma 0 comma 2 millimeter up. So plate is around 3.5 millimeter thick. So this will be enough for 2 millimeter move to avoid the penetration. So we done that. Now we'll put a mesh model. So first we'll go to bird mesh. Now we have splitted this into two half. We'll put some 10 just to get a better mesh. We'll use this algorithm. So I'll just go back. I'll show you. So you go this, assign mesh control. You click this. So here you use a mid-axis algorithm, and then you go to this element selection. You go in element selection. This is explicit analysis. So you select explicit 3D. Now this is very important step when you do SPH modeling. You select explicit. It's say C3D8R. You go down, conversion to particles. You say yes, time is equal to 0. That is what exactly you have to do. So once you done this solid mesh will be converted into particle. So This is very important step. I'll just repeat again. So you select explicit 3D, then you go here, conversion to particle. This is available from 6.12 onwards. I'm using 6.14, so it's available. And then you say conversion to particle, and you say yes. You done that. You quickly put a mesh. So you see quite a bit structural mesh you find here. So you got that. You go to aluminum now. Aluminum, you select around 15. This is just a demonstration problem, but then for accurate problem you go with a finer mesh, take a call based on your analysis. So you apply that. We can use chord structural, mainly chord structural mesh we will select. We'll also select, this will be the shell. Explicit, you have to select shell. You'll see here S4R, and then you quickly mesh it. So we're done both meshing. Now we'll define different things. We'll go to contact definition. So we'll first create a contact property. So friction, all this tangential behavior will say frictionless. It's a water body, so most of the time it is frictionless. And normal behavior, you say pressure over closure. Default one normal we are taken. We'll quickly create contact general. So just select a general contact. You don't know which part is going to come in contact, so take a contact general, all with self contact, and then you assign the contact property to that. We have done this. Quickly we'll create a BCs. So all these edges will select. So once you select first, then you put shift button. You select first, then you put shift button, then you can select all the edges. You say done, and then you put an end caster there, so it is fixed. Now we'll just do one more thing. Is for bird we need to create a set for these bird things. So we can create that bird set node. We'll select a bird. Done. We'll go to load. Predefined set, we'll select this initial velocity. You say go and select that set. We are going to give in -1000 meters per second, but you multiply by 10 power 3 to have a consistent unit. So you given velocity, everything. You define contact between this body, we assign everything. Now we'll go and create a step. Create a step for dynamic explicit analysis. Continue. It will be just 10 millisecond. Description bird strike. You can use mass scaling and all these options, but that is not required. So we are put for around 10 milliseconds. We'll just see how the bird hits and how the stress wave is generated. So we've done this. I'll save this as done. This will create a job. We'll write a file. So input data is written. We'll go for a data check. Let's check. Data check is a good option within Abaqus, where you can check if there is any error or anything. And we just submitted for data check. It will quickly give us whether there is any issue in terms of input given to the deck. If there is no issue, then it will say it's completed. So it's completed successfully. So I just quickly go and do one thing. I'll just submit a run. So I'll just go to C:. I'll just go and select the file. So this is the location. I'll just copy. Then I'll put ABQ 6145, that is version what I have, 6145. Then I'll put J is equal to job name is equal to, and then I'll just select that bird strike, and then I'll say CPUs is equal to 4 CPU I'm going to use interacting, and double precision I'm going to use. So guys, just I just go on and put on this command prompt just to show you. You put a double precision here, and then we'll just put enter. So yes, and that's where actually it's just going through input file. It go to pre.exe, it got package dot. So it started. Just wait for analysis to complete, and then once analysis is done, then we'll see. So it just started the analysis. So just wait. It's already started with the first step, so we can have a quick look on this, how it looks like. See, Abaqus bird strike. So let's see in some view. So it just started. It already hit the plate. So let me check where it has gone. It has gone to 11 steps. So let's see how it looks. So it's a easy, straightforward. You can see the bird hitting the plate. Plate also got deformed. It responded back, and then you can see the different things like how the stress is getting propagated within the plate. So guys, this was a simple problem to model. Again, the idea was to empower the Abaqus community to get into more into advanced modeling or technique like a smooth particle hydrodynamics. And let's see, it's completed. So let's check how it looks like for the. So this is for full 100 millisecond. Your bird is got hit, and then it's hit on the plate and the stress wave eroded. So just will you go to the last slide where you can see. So these are the references. You can see a lot of things where what we have to control. You go through the Abaqus documentation. Abaqus also have impact of water filled bottle problem, which you can use for understanding the smooth particle hydrodynamics. There are a lot of journals and proceedings available in terms of bird strike simulation. You can go through that. Quite a bit interesting references are there. You can use these to use a bird strike problem, and I think the current session what we have on the SPH will be helpful for you to do better learning with Abaqus software. Thanks a lot for watching this video. Don't forget to like us or subscribe us, Abaqus Acumen. Thank you. Bye bye.